and Francesco Pediconi from the Politecnico di Torino. And so we studied this special class of metrics on complex manifolds that are pluriclosed metrics with an additional condition that is the torsion of the Bismut connection being parallel. And at the end of the talk, essentially, we will see a classification for these manifolds. So the talk is divided in two parts. In the first part, we're called the basic definitions and, let's say, many results concerning pluriclosed metrics and the Bismut connection. And then in the second part of the talk, I will focus my attention in the case this Bismut connection has, let's say, good symmetries for the curvature tensor. And in particular, we will talk about Bismut-Kähler-like metrics. And then we will see a classification for this for manifolds having Bismut-Kähler-like metrics. And we will see how these metrics are related to pluriclosed metrics. All right, so the setting is Hermitian geometry. So during the whole talk, I will denote with M, J, G, omega, and Hermitian manifolds. So of course, I mean, M is a smooth manifold of real dimension 2n. With J, I will always denote a complex structure. So just let me recall that a complex structure is a 1-1 tensor, so an endomorphism of the tangent bundle that squares to minus the identity. And this is an almost complex structure. But then we ask for an additional condition that is the integrability condition that ensures that our manifold is indeed a genuine complex manifold. So we have local holomorphic coordinates. And I will denote with G an Hermitian metric that is a Riemannian metric that is compatible with J in the sense that J behaves like an isometry. And finally, I will denote with omega the fundamental form of the metric. So omega is a real positive 1-1 form that, if you want, is defined using G and J in this way. So omega is a 2 form, it's a differential 2 form, but it's of B degree 1-1 with respect to the B degree induced by the complex structure on the space of forms, right? Okay, so this is a Hermitian manifold. And of course, among Hermitian metrics, we have, we always look for special Hermitian metrics. And in this talk, let's say the most special metric we have is a Kähler metric. So let me recall that a Kähler metric is a Hermitian metric such that the fundamental form, that was the 2 form we had before, is D-closed. Okay, so D is the usual exterior derivative. And so omega, in fact, is a symplectic form. Okay, so on a Kähler manifold, we have essentially a complex structure, a Riemannian structure, and a symplectic structure that are compatible. And so that's why people usually say that Kähler geometry lies at the intersection between complex geometry, Riemannian geometry, and symplectic geometry. Okay, or in fact, we can also equivalently say that Kähler manifold is an Hermitian manifold such that the Levi-Civita connection, that is the unique metric connection without torsion, so the Levi-Civita connection preserves the complex structure. Okay, and actually this condition is the condition I'm interested in this talk. Okay, so these are Kähler manifolds, but of course, since we have all these very nice geometric structures that are compatible, we cannot expect Kähler structures to exist on every, let's say, complex manifold. And in fact, actually, we have obstructions to the existence of a Kähler metric, also at a topological level. Okay, so the Kähler geometry is very rich, but it's also somehow very rigid. So what I'm interested in is actually non-Kähler geometries. So the study of those, let's say, complex manifolds, or let's say Hermitian manifolds that do not admit any Kähler structure. Okay, so I'm interested in studying the geometry of these manifolds. Okay, so we have an Hermitian manifold. So I'm not assuming the metric to be Kähler. So in general, the Levi-Civita connection is not preserving the complex structure. So for this reason, somehow, if you want to study the non-Kähler geometry of your manifold, the Levi-Civita connection is not, let's say, the right connection to consider. And for this reason, one should maybe consider Hermitian connections. Okay, so an Hermitian connection is an affine connection that preserves the whole Hermitian structure. Okay, so what we have is that the connection is a metric connection, so it's preserving the metric, but it's also preserving the complex structure. Okay, but of course, this connection Hermitian connections will have torsion. Okay, in general. And what we have is this famous result of Goduchan saying that the result is true also in the non-integrable setting, but this statement is the statement in the integrable case. So on a Hermitian manifold, there exists an affine line of canonical Hermitian connections defined by this formula. Okay, so we have this connection depending on this parameter T, real parameter, and they are defined in terms of the Levi-Civita connection, plus we have these additional terms that essentially involve the torsion of the connection. And here you see again omega, that is the fundamental form of the metric. So actually sometimes I will call omega itself the Hermitian metric of the manifold. And we can see here this operator, dc, that is this, it's a differential operator that is defined using the exterior derivative d, and it's twisted by the complex structure J, okay? So we have the action of J, J acts on vector fields, but you can induce the action naturally on the space of forms. And so we have this differential operator that acts on differential forms, okay? Okay, so we have all these connections. They are Hermitian connections, but of course, in this, let's say in this line of connection, you can see immediately that there are two special connections that will correspond to the case t equal 1, where you get rid of this term, or t equal -1, where you can get rid of this other term, okay? And these two connections are the Chern connections and the Bismut connection. In particular, I'm interested in the Bismut connection that corresponds to the case t equal -1. So t equal -1, you don't have this term, and you just have this term, okay? We will see the formula later, but so the Bismut connection is the canonical Hermitian connection in the line that corresponds to t equal -1. And in fact, it's the unique Hermitian connection whose torsion is totally skew-symmetric, which means that if we define this tensor here, using the torsion of the Bismut connection and the metric, this is in fact a differential 3 form, okay? In the case of the Bismut connection. And well, of course, if omega is scalar, it means that omega is closed. And so if omega is closed, this term vanish, and so all these connections collapse to the Levi-Civita connection, okay? And so they all coincide with the Levi-Civita connection in the Kähler case. Okay, so we said for the Bismut connection, the torsion of the Bismut connection is a 3 form. And actually, you can check, it's a very easy computation to show that this 3 form is just up to sign the dc of omega. So again, omega is a 2 form, is the Hermitian metric, and dc is increasing the degree by 1. So we have this 3 form. But this 3 form is not closed in general. And in fact, an Hermitian metric is called pluriclosed if the torsion of the Bismut connection is a closed 3 form. Okay, so if the torsion is closed. And equivalently, since the torsion actually is just the dc of omega, we are just saying that ddc omega is equal 0. Or, if you prefer to use the operators del and del bar in complex geometry, we are saying that omega is dd bar closed, okay? So these are pluriclosed metrics. In the literature, sometimes they are called SKT, which means strong Kähler with torsion. So, in the literature, there's a very rich literature about these metrics, And sometimes they are called pluriclosed, and sometimes they are called SKT, but they are just the same. I mean, it's the same definition. Omega is a DDC closed. And clearly, if you have a Kähler metric, it means that omega is closed. In particular, it is also DDC closed. And so Kähler metrics are pluriclosed. Okay, so the pluriclosed condition is a more general condition than the Kähler condition. Okay. So, of course, one question is, do we have examples? Okay, not every, I mean, every complex manifold admit Hermitian matrix, but do complex manifolds admit pluriclosed matrix? In order to answer this, let me first recall another definition that is the definition of Goduchon metric. An Hermitian metric is called Goduchon if it satisfies this equation. So here we are, n is the complex dimension of the manifold. During the whole talk, n will be the complex dimension of the manifold. So we are taking the wedge product of omega with itself, n minus 1 times, and then you apply d and dc to this metric, to this, to omega n minus 1, and then you get 0, in the case the metric is Goduchon. So you can see immediately that if we are on a surface, complex surface, n is equal to, so this equation just reduced to the case DDC omega being 0. So Goduchon metrics on surfaces, on complex surfaces, are just pluriclosed metrics. But what we have is this famous result of Goduchon that ensures that if you have a compact complex manifold of dimension greater than 1, then Goduchon matrix always exists. Actually, the result is finer because they say that Goduchon says that there exists a Goduchon metric that is unique up to multiplication with positive constants in the conformal class of any Hermitian metric. So if you have a compact complex manifold and you fix an arbitrary Hermitian metric, in the conformal class, you have a Goduchon metric. So this means that since Goduchon matrix always exists on compact complex manifold, then on compact complex surfaces n equal 2, it means that pluriclosed matrix always exists. But of course, the situation in higher dimension is very different. So the problem is...
there is a question by Enrique.
Can I, real quick, on the previous slide?
Yes. Sorry.
Yeah. So I don't see uniqueness here. Do you know anything? Do we know anything about uniqueness of Goduchon matrix?
Yeah, I mean, if you fix an Hermitian metric in the conformal class, the Goduchon metric is unique up to multiplication with a constant, with a positive constant.
Okay.
Okay. Yeah. You have uniqueness. You have uniqueness because we have n greater than 1, of course.
Aha. Oh, I see. It is here. Okay.
Yeah. But you need compactness. And actually, if I remember correctly, this result also holds in the non-integrable setting for an almost complex manifold. You can still define the operator DC. You have an almost Hermitian metric. You can define this equation, and yeah.
Right. Thanks.
Okay. Okay. So what about higher dimensional examples? Okay, because we have, so in dimension 2 we always have pluriclosed matrix. What about higher dimensions? So of course, I mean, here there is a list of results. Of course, it's not a complete list. I mean, there are a lot of results about pluriclosed matrix, a lot of examples. So here there are just a few. Okay. So first of all, let me say that if you have an even dimensional compact Lie group, there is this Samuelson construction that ensures that you can construct left invariant complex structures on these Lie groups. And it turns out that if you have a compatible B-invariant metric, this metric has to be pluriclosed. Also, Andrade and Tolkakier studied the products of, let's say, three-dimensional Sasaki manifolds. You can construct, so first, a Sasaki manifold is, let's say, the odd-dimensional counterpart of Kähler manifolds. I mean, a Sasaki manifold is an odd-dimensional Riemannian manifold whose metric cone is scalar. And on this, if you take products of three-dimensional Sasaki manifolds, there is, let's say, a natural way to construct complex structures there. And you can show that you can find examples, let's say, with pluriclosed matrix. And many examples actually come from quotients of Lie groups, especially nilpotent or more in general solvable Lie groups. So there are many results in this direction. Okay, so we have nil manifolds or solved manifolds, and there are a lot of examples of let's say solved manifolds, maybe with a special complex structure and that admit pluriclosed matrix. And if you go to low dimensions, then you can also find classification results. For instance, there is this result due to Fino-Parton-Salamon that is special to dimension 6 in the nilpotent case. So suppose that you have a nilpotent Lie group with a left invariant complex structure and in dimension 6, then Fino-Parton-Salamon showed that either all the Hermitian matrices are pluriclosed or none of the matrix is pluriclosed. So essentially the information on the existence of pluriclosed matrix is encoded in the complex structure. But this is, again, very special to the nilpotent case and dimension 6. Then there are other, as I said, other characterization on special solvable Lie groups like almost abelian Lie groups, this was done, for instance, by Arroyo Lafuente. So, I mean, there are many, many examples. Also, if you want to construct new examples, there are some techniques. For instance, first, Fino and Tomassini showed that if you have a manifold minus a point with a pluriclosed metric, then actually you can extend the metric to the whole manifold. And also, they showed that you can construct new pluriclosed manifolds using blowups. I mean, so if you start with a compact complex manifold and with a pluriclosed metric, and you perform a blowup at a point or along a compact complex manifold, then the new manifold you construct is still pluriclosed. So you can construct new examples, but unfortunately, you cannot construct new examples using small deformations. Again, Fino and Tomassini proved that if you have a compact complex manifold with a pluriclosed metric, and you deform a little bit the complex structure, so you construct new complex manifolds, but these new manifolds in general will not have a pluriclosed metric, okay? So you cannot construct new examples in general, I mean, in general, using small deformations. Also, in complex geometry, as I said, we have, I mean, there are several possible generalizations of the Kähler condition. So there are several special Hermitian metrics that can be studied. And it is a natural question to understand whether on non-Kähler manifolds, different types of metrics can coexist on the same manifold, okay? And it turns out that the pluriclosed condition is complementary, if you want, to the balanced condition. So let me just recall what a balanced metric is. So a balanced metric on a complex manifold is an Hermitian metric satisfying this equation. So what does it mean? I'm taking the wedge product of omega with itself n minus 1 times. I apply the differential d, and it turns out that this form is 0, okay? So the omega n minus 1 is closed. Or equivalently, if you look at the first equality here, on every complex manifold, if you take an Hermitian metric, you have this equality. For every Hermitian metric, you take the differential of omega n minus 1, and it will be equal to theta wedge omega n minus 1, where theta is a 1 form, okay? And it's called the Lie form of the metric. So balanced actually means that theta is actually 0, okay? So the Lie form is 0. So what does it mean that the pluriclosed condition is complementary to the balanced condition? In the sense that if you have an Hermitian metric, omega, that is both pluriclosed and balanced. So omega at the same time is satisfying the equation for DDC omega being 0, that was pluriclosed, and the balanced equation, that is this one. then omega has to be Kähler. And Alexandrov and Ivanov proved this result using this formula. There are actually alternative proofs. But the thing is, so why this is true? Because if omega is pluriclosed, it means that DDC omega is 0. So here in this equation on the left-hand side, we have 0. And on the right-hand side, what we have, omega is also balanced, which means theta is 0. So here, this is 0, and also this term is 0. So see, we are left with the norm of the omega square being 0, so which means that omega is closed, which means omega is a Kähler metric. Okay, so if omega is at the same time pluriclosed and balanced, then it is Kähler. But actually, it seems that this is more general than that, in the sense that Fino and Vezzoni have proposed this conjecture that says that actually on a compact complex manifold, if you have a metric that is pluriclosed and a second metric that is balanced, then the conjecture is saying that there has to be a third metric that is Kähler. Okay, so in a sense, this is saying that if you have a non-Kähler manifold, you cannot have both pluriclosed matrix and balanced matrix. I mean, these two types of matrix cannot coexist. And of course, here I just put a list of evidences, but of course, all the examples we have of pluriclosed manifolds or balanced manifolds, of course, satisfy this conjecture. It's still open. It's still an open conjecture. And usually, every time a new examples of a pluriclosed manifold or of a balanced manifold appear, people usually try to check whether this conjecture is true or not. And here, of course, most of the examples are quotients of nilpotent or solvable Lie groups, but also the conjecture is known to be true in many other cases, like manifolds in class C of Fujiki and so on. Okay, so this is just a brief, let's say, overview of pluriclosed matrix. So let me go back to the Bismut connection. So the Bismut connection, we said, is the unique Hermitian connection whose torsion is totally skew-symmetric. And we said that the torsion is minus dc omega. And the Bismut connection was related to the Levi-Civita connection through this formula. And again, the Bismut connection does not coincide with the Levi-Civita connection unless the metric is a Kähler metric. Okay, so for this reason, we can, since the Bismut connection differs from the Levi-Civita connection, we cannot expect the same, let's say, nice symmetries, for instance, for the curvature tensor. And indeed, the Bismut connection does not satisfy let's say, the torsionless first Bianchi identity, meaning that if you take the curvature tensor of the Bismut connection, and you consider cyclic sum over, let's say, x, y, z, here x, y, z, u are vector fields, then this is not 0, okay? But we have terms involving the torsion of the connection, okay? In particular, we have the differential of the torsion, and if you remember, a metric is pluriclosed when this is 0 by definition, okay? So the differential of the torsion is 0 by definition when the metric is pluriclosed. And also we have a term here that involves, let's say, the parallelism of the torsion, okay? Okay, so this somehow motivates the following definition. So this definition is due to, that is written here, is due to Angelo Talogarte Viacampa, and it's a definition for a metric connection on a complex manifold. The metric doesn't have to be an Hermitian metric. So you just have a complex manifold, a Riemannian metric, and a metric connection. And they say that a metric connection is scalar-like if it satisfies these two conditions. So the first one is the first Bianchi identity. And the second one the J invariance in the first two entries and the second two entries. Is there a question?
Yes.
Yes.
Yeah.
Sorry, because I cannot see anyone. So.
Yeah, it's usually me. I was just more annoying than average. Can you go back one slide, please? Just your nablet T has captured my attention. So, supposing in the pluriclosed regime, so as you just said, the first term on the right-hand side is 0, right? And so you're left with nablet T. What happens if is there of any particular value to you if nablet T is totally skew like it defines a 4 form? Is that a special regime? Right? Because nablet T doesn't have to be a 4 form, right? It could.
Right.
Like, if it does that have a special meaning in your context?
It will. I mean, we will see exactly how these three conditions are related. I mean, the vanishing of this part on the left-hand side, the vanishing of this, and for instance, the vanishing of this. That is somehow related to your question, I think.
Right. So, yeah. It's a weaker version of that question. I'll wait until you finish. Yeah.
What I know the answer of is the case when we have, let's say, two of these that are 0. That's what I know.
I see. I'll ask this again then.
So I will talk about this, and I will also say a few words about actually, unfortunately, the proof. How does it? I mean, we'll see in a moment. So if I will not answer your question, you can ask me again in that case. Okay.
Thanks. Deal.
Okay. Thank you. Okay, so we were saying, so we have a metric connection, and this connection is called Kähler-like if it satisfies these two conditions. So we said we have the first Bianchi identity and J invariance in the first two entries and second two entries for the curvature tensor. And of course, the name Kähler-like come exactly from the fact that in the Kähler case, we have all these symmetries, okay? So we are saying that we want this metric connection to have Kähler-like symmetries, okay? But actually, the Kähler-like definition was originally given by Yang and Zhang for the Levi-Civita in the specific case of Levi-Civita connection and Chern connection. And in those two cases, if you take one of these two connections, the Kähler-like definitions you have here reduces to the definition of Yang and Zhang, okay? And so what I want to discuss in a moment is what is definition in the case I want to consider this the Bismut case, okay, the case of the Bismut connection, okay? So now assume that we have an Hermitian connection. So the connection is not just preserving the metric, but also the complex structure, and assume that the metric is an Hermitian metric. Then you can check. It follows immediately from the definition of curvature tensor that we have J invariance in the last two entries, okay? Then also, if you assume that you have the first Bianchi identity, then what we have is that we can swap. I mean, you can apply the first Bianchi identity, I think, 3 or 4 times to show that you can swap the first two entries and the second two entries in the curvature tensor. Okay, you have xy, zw, that, and you have here zw, xy. Okay, so what does it mean? It means that if you take one of the Godushan connections that we saw before, so they are Hermitian connection, and assume that for one of the Godushan connection, we have the first Bianchi identity, then for this reason, we have J invariance in the first two entries, but then you can swap, because we are assuming the first Bianchi identity, you can swap the first two entries with the second two entries, so you get also J invariance in the first two entries, okay? So this means that in the previous definition, the second line is free, okay? It's given for free. So for us, since I'm for the Bismut connection, the definition of being Kähler-like actually reduces the first Bianchi identity. So we will say that the Bismut connection is Kähler-like if it satisfies the first Bianchi identity, okay? And right, and also in case you're interested in the literature, sometimes this condition is called the Strominger-Kähler-like, because sometimes the Bismut connection is also called the Strominger connection, okay? And probably in the following, I will say that the Hermitian metric is Bismut-Kähler-like, which just means that the associated Bismut connection is Kähler-like, okay? So we have the first Bianchi identity. Okay, just a few words about other cases. Suppose that your manifold is compact, then Yang and Zhang proved that if either the Levi-Civita connection or the Chern connection is scalar-like, then the Hermitian metric is balanced, okay? So balance is in the definition I gave before, in the sense that the differential of omega and -1 is 0. And then Lafuente and Stelfield proved that if you take a Goduchan connection, nabla T, so we have this line of connection, you take one of these connection, except for Chern and Bismut connections. If you assume that nabla T is scalar-like, then they prove that the metric has to be Kähler. Okay, so we have this line of canonical Hermitian connection, and you have the Bismut connection and the Chern connection there. So if you take the Chern connection and you assume that it's scalar-like, the metric is balanced. If you take any other metric, connection except for Bismut and Chern, then you get a Kähler metric. And yeah, and so we are left with the Bismut connection. So again, you can see here these three metrics appearing: the balance metric, pluriclosed metric, and Kähler metric, just like in the conjecture of Fina and Mazzoni. So, so what about the Bismut connection? In the same paper where Angelo Talugarte Villacampa defined the Kähler-like connections, they proposed they brought this conjecture saying that if the Bismut connection is scalar-like, then the metric has to be a pluriclosed metric. So this means that if we have the first Bianchi identity for the Bismut connection, then the metric has to be pluriclosed. And the evidence is, if I remember correctly, in that paper where this, so the first is the obvious one. Of course, if you have a flat, so if the Bismut connection is flat, which means that the curvature is 0, the Bismut curvature is 0, then clearly we have the first Bianchi identity, so of course it's Bismut Kähler-like. And in that case, it is known that the metric is pluriclosed. Actually, Bismut flat manifold have been studied by Wang Yan Zhang, and they are covered by this, let's say, even-dimensional Lie groups of this type. So you have a Euclidean factor and a compact semi-simple Lie group, K. And these are endowed with the Samuelson complex structure and the compatible B-invariant metric. And the compatible B-invariant metric is known to be pluriclosed. And they are Bismut flat. And they also had other examples confirming the conjecture. So with Annafino, we tried to study this conjecture, but unfortunately, we were not able to prove it. But what we did is exactly in this formula, in this formula here, try to understand a little bit the relation between the first Bianchi identity, that is the vanishing of this, the pluriclosed condition, that is the vanishing of this, and the parallelism of the torsion. And so what we proved is that these are related. I mean, essentially, for instance, if you have a pluriclosed metric with the first Bianchi identity, then the torsion is parallel. Or on the other side, if the torsion is parallel, then the condition of being Bismut Kähler-like and pluriclosed are equivalent. And if you put together these two results, essentially you have this. So suppose that you have the first Bianchi identity, then the metric is pluriclosed if and only if the torsion is parallel. Okay, And we proved these results using, let's say, formulas like the one I showed before, okay? So in these intrinsic formulas involving torsion, curvature, tensors, and so on. And but you see, this is not proving the conjecture. We are just saying that the pluriclosed condition is equivalent to the parallelism of the torsion. In fact, the results, I mean the conjecture, have been proved by Zhang and Zhang using different techniques, using a coordinate approach. So Zhang and Zhang proved that not just the conjecture, but actually they were able to characterize completely the Bismut-Kähler-like condition. So your metric is Bismut-Kähler-like, which means, again, we have the first Bianchi identity for the Bismut connection. If and only if the metric is pluriclosed and the torsion is parallel. Okay, so we have not just the conjecture, but we really have a characterization. And I think that this is the best we have for using the formula I showed before. But again, actually their proof is not using these formulas. They use a completely different approach. They use a coordinate approach. And I'm not sure, I mean, I'm not aware of any other proof of these results. And also, so Bismut-Kähler-like matrices are pluriclosed matrices. So again, every time we have a manifold, let's say with a pluriclosed matrix, we said that we check whether we also have a balanced matrix because we have this conjecture of Fino-Bezzoni. And Zhang Zhang proved that the conjecture holds also for this manifold. So if you have a compact non-Kähler Hermitian manifold and a Bismut-Kähler-like metric, which is in particular pluriclosed, then there are no balanced metrics. Okay, so again, the conjecture is confirmed. And actually, they showed something stronger. They showed that there are no, not just balanced metrics, but there are no strongly Go-Duchon metrics. This is another possible generalization of the Kähler condition. Actually, this is even more general than balanced. Okay, so what are these metrics? So now, Bismut-Kähler-like matrices are just pluriclosed matrices with parallel Bismut torsion. That is, and it's the object of my talk, pluriclosed manifolds with parallel Bismut torsion. So we are interested in these matrices. And in fact, in dimension 2, complex dimension 2, these matrices are already known. So let me recall this definition. So an Hermitian metric is called Weismann if it is locally conformally Kähler. So locally conformally Kähler means that if you take the differential of your metric, omega, this is not 0, okay? 0 means scalar, but it's equal to theta wedge omega, where theta is a declosed one form, okay? It's actually a multiple of the Lie form. And so these metrics are called locally conformally Kähler because you can actually check using the definition that actually locally your metric is conformal to a Kähler metric, okay? But the Weismann metrics are a little bit more, so they're not just locally conformally Kähler, but actually this one form theta is Levi-Civita parallel. So it's not just declosed, but it's Levi-Civita parallel. Okay, so for Weismann, we have these two conditions. And it turns out that Weismann metrics are Go-Duchon metrics. They are Go-Duchon. Go-Duchon metrics were the metrics we saw at the beginning of the talk. So they are defined by this equation saying DDC omega n minus 1 is 0. But the point is that it's not important to remember the definition. The important fact about Go-Duchon metrics is that they always exist. Okay, and Weismann metrics are, in particular, they are Go-Duchon metrics. Okay, and so why am I talking about Weismann metrics? Because in dimension 2, the torsion of the Bismut connection, so if we are on a complex surface, the torsion of the Bismut connection is dual to the Lie form theta. So here star is the Hodge star operator of the metric, And theta is the form appearing in this definition. So if we are on a Hermitian surface, actually it turns out that the metric is Weismann if and only if it is Bismut-Kähler-like. And again, Bismut-Kähler-like by Zhao and Zhang means that the torsion is closed and parallel. Okay, so Weismann metrics are exactly Bismut-Kähler-like metrics. Okay, they coincide. So Bismut-Kähler-like metrics, I mean, are very well known in dimension 2. And actually, in any dimension, Andrade and Villacampa proved that there is an implication that, so if we have a Weismann manifold in general, then the torsion is, the Bismut torsion is Bismut parallel, okay? So we have always this condition. So if we have Weismann here in any dimension, this condition is given, the parallelism of the torsion. The problem is the first condition, that is the closure of the torsion. This condition is the definition of pluriclosed metric. But if you remember, in dimension 2, pluriclosed metrics are Goduchon metrics. So pluriclosed metrics always exist, okay, in dimension 2. And we said that Weismann metrics are Goduchon metrics. So in dimension 2, Weismann metrics are pluriclosed metrics. Okay, so in dimension 2, the implication Weismann implies this is obvious. And the other one, for instance, is true in any dimension, as shown by Andrade and Villacampa. But the problem is what happens in higher dimension to the implication Weismann implies pluriclosed. And we will see this in a moment. Let me also say that Andrade and Villacampa proved that the converse is true in the case you assume that the metric is locally conformally Kähler. And actually, the locally conformally Kähler condition is related to the Kähler-like condition. Because, for instance, on a Hermitian surface with the Annafino, we showed that if we do not assume the whole, the Kähler-like definition, but something weaker, that is the J invariance in the first two entries, then we can prove that the metric is locally conformally Kähler. Okay, so it is locally conformally Kähler, and then if you assume something stronger, that is the Kähler-like condition, you actually get a Weismann metric. Okay, so what about examples of Bismut-Kähler-like manifolds? Of course, we have Weismann surfaces that in the compact case are classified by Belgun. We have Bismut flat manifolds that we already mentioned. Of course, if the curvature is 0, then we have the Kähler-like condition. We have all the Kähler-like symmetries we want for the curvature. And they are known, so they are Bismut-Kähler-like. And then, we constructed some examples using Lie groups, almost abelian Lie groups. And again, unfortunately, we cannot construct new examples using small deformations. I mean, if you start with a compact complex manifold that is Bismut-Kähler-like, and you deform the complex structure, in general, the new complex structure will not admit Bismut-Kähler-like matrix. But again, so what about higher dimensions? So, we said that in dimension 2, Bismut-Kähler-like and Weismann coincide. What about higher dimension? They do not coincide. Actually, this Weismann matrix and pluriclosed matrix cannot coexist on compact complex manifolds. So this is a result due to Angel and Othman. Okay, so if you have a compact Weismann manifold, starting from dimension 3, we cannot have pluriclosed matrix. So in particular, we cannot have Bismut-Kähler-like matrix because Bismut-Kähler-like matrix are in particular pluriclosed matrix. Okay, so that's why I said in this implication, this is true just for dimension 2, because for instance, we said Weismann in dimension 2 implies this just because pluriclosed metrics are Goduchon metrics. Okay, and so Weismann metrics being Goduchon, they are pluriclosed on surfaces. But in higher dimension, Weismann will never imply the torsion being closed. Okay, so because we cannot have Weismann metrics and pluriclosed metrics. So what are Bismut-Kähler-like manifolds in higher dimension? Okay, so in order to answer to this, first, I will need this construction that we give with Giuseppe Barbaro and Francesco Pediconi. So it's a construction of Bismut-Kähler-like manifolds. And we will see that essentially up to passing to the universal cover, all Bismut-Kähler-like manifolds come from this construction. Okay, so let's fix SI to be a three-dimensional Sazakian manifold. I goes from 1 to S, let's say. So we are fixing the Sazakian structure, okay? We said that Sazaki manifolds are odd-dimensional Riemannian manifold whose metric cone is scalar. And in particular, we are taking three-dimensional Sazakian manifolds. And on these manifolds, we always have this special vector field that is a unitary killing vector field that is called the Reeb vector field, okay? And then we have this an orthogonal distribution that is a two-dimensional distribution on these manifolds. And okay, so we have these manifolds. Then we take K to be a compact semisimple Lie group of rank R, endowed with a B invariant metric. And then we fix a natural number, L, such that if we take L plus the number of Sazakians plus the rank of the group, we want this number to be even, let's say 2m. And then L cannot be too large, okay? So let's say L cannot be too large. Okay, so then we take this product. We take our L with the Euclidean structure times the Sazakians times the Lie group, okay? And we want this manifold to be even dimensional, let's say 2n. Okay, so we take this with the product Riemannian metric, okay? So we have the Euclidean metric, the Sazakian matrix, and the B invariant metric on the Lie group. Okay, and on these manifolds, we construct a complex structure as follows. So let's take a frame, global frame, let's say H1, HL for RL. And then on each Sazakian manifold, we take the Reeb vector field, okay? And we call this vector field HL plus 1, HL plus S. And then fix a maximal torus of K with a frame that goes from HL plus S plus 1 to HL plus S plus R that was 2m. Okay, so we define an almost complex structure in this way. So we call this structure standard. So we want that this distribution is, the distribution spanned by these vectors to be J invariant. Then on each Sazaki manifolds, we have this transverse distribution that is endowed with a complex structure. Naturally, it comes from the Sazaki structure. So we want our complex structure to coincide with this transverse complex structure for each Sazaki manifolds. And finally, we are left with what happens outside the torus. Let's say, so J, we want that projection to a K invariant complex structure on K over T. And it turns out that this is an Hermitian manifold. Okay, so you have to check that this complex structure, this almost complex structure is integrable and that it's compatible with the product metric. I should say that actually this constructor generalizes a couple of constructions. One is without the factor K, these are L times the three-dimensional Sazakians that appears in a paper of Zhao and Zhang. And the other one is without the Sazakian factors, and this is essentially comes from the Samuelson complex structure compatible with a B invariant metric. Okay, so this is a generalization of two known constructions. And the result is the following. So suppose that we have a complete, simply connected Hermitian manifold. Then this manifold is pluriclosed with parallel Bismut torsion, which means Bismut-Kähler-like. So if you want, thanks to Zhao and Zhang, this is the validity of the first Bianchi identity for the Bismut connection, these two. So we have this if and only if it decomposes as a product of Hermitian irreducible factors, and these factors are either Kähler or non-Kähler. Of course, we can always have Kähler factors. The Kähler factors, of course, are Kähler-like. Okay, so we can always have these Kähler factors. So what are the non-Kähler factors? Well, the non-Kähler factors are described by the previous construction. Okay, so are Hermitian manifolds of this type. Okay, and this is in any dimension. Just few words about the proof. One implication is a computation. Okay, so we need to check that. I mean, the Kähler factors, of course, are pluriclosed with parallel Bismut torsion. The thing is to show that these factors are pluriclosed with parallel Bismut torsion, and so this is a computation. Okay, so what about the other implication? So the idea is roughly the following. So you have a metric that is pluriclosed, so the torsion of the Bismut connection is closed, and it is parallel. Okay, so we have these two conditions, and so using these two conditions, you can check that the torsion of the Bismut connection satisfies the Jacobi identity. Okay, so essentially on each tangent space, we have a Lie bracket given by the torsion of the Bismut connection. Okay, but then the torsion is parallel, and so you can show that what you have is that all these Lie algebras are isomorphic, and in fact we have a Lie algebra bundle on the tangent bundle. Okay, but the Lie bracket now is given by the torsion of the Bismut connection. Okay, so now you have to check that this Lie bracket is compatible with the complex structure and the metric. So you have to check that indeed J is integrable with respect to this Lie bracket, and we have a B invariant metric, okay, on this on the fibers. Once you have done this, so you have this compact Lie algebra, and so there is this result of Pitti saying that the complex structure has to be a Samuelson complex structure. I mean, Pitti shows that all complex structures on compact Lie groups have to be of a as in the construction of Samuelson, that is done using a root space decomposition. But you have this on each fiber, so you have to check that this decomposition on each fiber actually gives a decomposition, a Bismut parallel decomposition for the tangent bundle. Okay, so you have to do this. And then using some curvature computation, you show that this decomposition actually leads to a Levi-Civita parallel decomposition for the tangent bundle, and so you get a de Rham decomposition for the manifold. And then once you have the decomposition of the manifold, you have to check what are these de Rham factors. And what happens is that essentially you separate the Bismut flat part from the non-Bismut flat part. And it turns out that the non-Bismut flat part corresponds to ideals of rank 1 that corresponds to the three-dimensional Sasaki manifolds. And the remaining part that is Bismut flat, due to a result of Cartan-Schauter, is a Lie group with a B invariant metric. Okay, so these are, let's say, roughly the steps of the proof. Okay, so what about this result? Actually, this result was already known up to dimension 5. So, I mean, this result was known for surfaces. That was the Weismann case. So what about higher dimension? So actually, Yao, Zhao, Zhang proved that result in dimension 3, and Zhao and Zhang proved that result in dimensions 4 and 5, because essentially the previous result is classification result, because you can take now the classification of compact simply connected simple groups, and in each dimension you can check all the possible products that you can have with RL times the three-dimensional Sasaki manifolds times this compact semi-simple Lie group, right? And so, and we have some restrictions. So if you remember, sorry, I'm jumping back and forth. So this L cannot be too large, we said. So RL cannot be too large. Otherwise, it wouldn't be Hermitian irreducible. And so, for instance, in dimension 3, if you have a complete Bismut-Kähler-like manifold, okay, so pluriclosed with parallel Bismut torsion, that is full. Full means that in the Hermitian universal cover, you don't have Kähler factors. Because we said that we can always have Kähler factors. Of course, they are Kähler-like. And so we don't want these Kähler factors. Otherwise, you would have a Kähler factor and something else that is of low dimension. So you look at the classification in low dimension. Okay, so assume that in the universal cover, we don't have Kähler factors. Then in dimension 3, the universal cover is holomorphically isometric to the product of two three-dimensional Sasakian manifolds. Okay, with the Hermitian structure we said before. Okay, and again, we cannot have something like R3 times a Sasakian manifold, otherwise, because it's not Hermitian irreducible. Okay, so we said that the Euclidean factor cannot be too large, and so we can just have the product of two three-dimensional Sasakian manifolds. And then Zhao and Zhang proved this result in dimension 4 and 5. So for instance, in dimension 4, complex dimension 4, we have this group that is Bismut flat, and this other manifold are 2 times the product of two three-dimensional Sasakian manifolds, and this is not Bismut flat. And then similarly in dimension 5, they got this and this that are Bismut flat, and this other one that is not Bismut flat. So 2 comments. First, this result is up to dimension 5. I mean, the proof of Yao Zhao Zhang and Zhao Zhang is based on, they have this coordinate approach, just like in their general result for Bismut-Kähler-like matrix. And so it works up to dimension 5. But you see that here, in all these, let's say, cases, we never have the 3 ingredients in the decomposition. So in this product, we have an Euclidean part, the Sasakian, and the Lie group. But here, up to dimension 5, we never have all these 3 ingredients. We have either the Euclidean part with the Sasaki groups, or, with the Sasakian manifolds, or a Lie group times the Euclidean factor, okay? So we never have all these 3 objects. And indeed, the first dimension where we have all these 3 objects is dimension 6. So, for instance, we wrote down the classification in complex dimension 6 of a complete Bismut-Kähler-like manifold with no Kähler factors in the universal cover. And so the non-Kähler factors of dimension 6 have to be of this type. So either you have just Sasakian manifolds, and this is not Bismut flat, or you have R3 times 3 three-dimensional Sasakian manifolds, and this is again non-Bismut flat. Or you can have R2 times this group, and this is Bismut flat. Or here, so the dimension 6 is the first time you have R times a three-dimensional Sasakian manifold times a group, okay, a Lie group. But the first time you have this is in dimension 6. And of course, you can wonder what happens in higher dimension. And of course, you can look at the classification of the groups and write down all the possible cases. But let's say that the dimension 6 is the first dimension where we can really see these three bricks in the non-Kähler pluriclosed with parallel Bismut torsion factor. Okay. Yeah, and I think I can stop here. Thank you.
Thank you, Nicoletta, for a very nice talk. Can you see us now?
Yes.
Okay.
Finally.
Well, thanks. Well, are there any questions? I guess Enrique has something to say.
Yeah. So going back to that point, can we have a look together at the definition of Kähler-like?
Oh, sorry.
Of Kähler-like.
Oh, yes, of course.
It's the same spot where I might have stopped you the first time. Because
this one.
Still seeing the thank you screen.
Yes, it hasn't changed.
It's not changing? No. Okay. So I stopped the share because
now you're good.
Now
yes.
Can you see?
Yes, yeah, we can see it now.
Perfect. And can you see the definition of Kähler-like?
Yeah.
Okay.
So, yeah, thanks. So I was just trying to understand. So Kähler-like means first Bianchi and J invariant, right?
And this, yeah, and these two, yes. Mm-hmm.
What about the alternation of indices? Yeah, the pairwise, let's say, Riemann-like property of the tensor.
Yeah, I don't know. I'm not aware of yeah. No,
because
I don't know. I mean, the only definition I have in mind of asking for symmetries are this. I mean, and this is actually the more general I have in mind, actually, of Kähler-like. I mean.
Yeah, do you want to have a look? So let me just suggest something which is related to what my student Agnaldo Silva is studying. So maybe I think there's a slide just before this one. Can you go up?
Sorry?
Can you go up to the formula where you write, the general Bianchi term equals dt plus another t?
I changed the slide. Can you see it or it doesn't move?
Okay. Maybe if you take it out and then you go back now.
And then
there. Yes.
And now you can see it. Okay.
Yeah. Right. So let's stay in the pluriclosed domain, right? So the first term is 0. On the right-hand side, yeah? So we could have a weaker version of first Bianchi, which is just, the term on the left-hand side equals nabla t, yeah? Now, the condition for the Bismut curvature to be Riemann-like is that nabla t is a totally skew 4 form. Right? The way you prove it is the way you would for any 4 tensor, right? As you do it for the Riemann tensor, you totally symmetrize the left-hand side, so you get 4 equations, and then you sum them all, you get 12 terms, 8 of them die, 4 of them remain, but they're equal 2 and 2, so that's how you conclude the symmetry of the Riemann tensor, for instance, the pairwise index symmetry, right? Now, if you have first Bianchi, then you can do this 4 times by getting 0 on the right-hand side. If you don't have first Bianchi, but the right-hand side is totally skewed, you don't get 0 at each of these 4 equations, but you do get at the end, because you have totally symmetrized. So if nabla t is totally skewed, you do get 0 at the end of it. So the proof still works. And so it would appear to me that in the pluriclosed setting, a natural weaker condition that sort of stratifies the problem is, which is weaker than parallel Bismut, is when Bismut nabla T is totally skewed. This would mean that the Bismut curvature tensor has the Riemann symmetry. Never mind, because we already studied the J invariance, right? I saw one of your partial results at the end. I say, what if you just impose J invariance? Well, you could just impose, just as you do that, you could just impose Riemann-like being Riemann-like, right? And this would be sort of weaker still sort of layer of a very similar problem. One could think of a next paper called Pluriclosed manifolds with a nabla T, with totally skew nabla T.
Yeah, right. Mm-hmm.
Do you agree? Do you know that anyone else is thinking about this?
I don't think so. I mean, I'm not aware of anyone asking for pluriclosed plus nabla T being totally skew. No.
If we manage to write something, do you think you could have a look? Because this is referring to some work by one of my students. It would be very nice if you could comment on it.
I think so. Maybe, I mean, one could try to understand what this condition would mean. Yeah, I'm not sure. I mean, I never checked, so I cannot really give you like immediately an answer of this. But yeah. I think there are many people looking for the parallelism of the torsion, not really the totally skew for the nabla T. No. I mean, there are many papers on maybe not pluriclosed, but just look for torsion of the Bismut connection being parallel, and maybe with some additional conditions, and then there are some results. But in the other case, I don't know.
Okay, that's relieving, right? There's a student. One of my students is thinking about this. If you told me, I'm a Fino and even I solved this in 2001, that would be disappointing. But thanks. It's good to know.
Mm-hmm.
All right, cheers.
Okay, I guess Paul Schwan has a question.
Yes, I do. Hi, Nicoletta.
Hi.
Suppose we have a Bismut connection with parallel torsion, so Kähler-like or not. Is there anything we can say about the holonomy representation or the stabilizer of the Bismut torsion?
Maybe, I don't know, maybe Adrian knows better than me this, without us, I mean, because if you assume, I can answer this better if you assume that the pluriclosed condition in addition, because in that case, for instance, the vanishing of the Bismut-Ricci form, I mean, the Bismut, in that case, the Bismut-Ricci form completely determines the curvature of the Bismut connection for the Bismut in the Bismut-Kähler-like case. So in that case, yes, and actually one knows exactly. So when we have the vanishing of the Bismut-Ricci form, we know exactly what happens. You have Kähler-Ricci factors times these Bismut flat factors essentially. And in that case, we have, I mean, holonomy in S1. But if you just assume the parallelism of the torsion, I don't know.
Right, yeah. I mean, suppose the Kähler-like case, you could maybe read it off this decomposition theorem somehow.
I mean, yeah, if you have the Kähler-like case, you have this decomposition theorem. And then, for instance, I mean, you can show that actually, so the Bismut-Kähler-like manifolds are very close to be Bismut flat, actually. So so let me go back to the decomposition here. So can you see the theorem with the decomposition?
Yes.
Right, so this is the Riemannian product, but it's not necessarily all.
This is Hermitian irreducible. Yeah, and the thing is that with this structure, actually, the only non-Bismut flat part, I mean, it's very close to be Bismut flat. The only non-Bismut flat factors are given by the Sazakian manifolds. And actually, it's given by the transversal distribution in the Sazakian manifolds. These are the only, let's say, components giving non-trivial curvature. Okay, everything else in all the other cases, the curvature tensor vanishes. But this is in the pluriclosed with parallel bismuth torsion.
Cool. The reason why I was asking is because there is for geometries with parallel skew torsion,
yeah,
symmetric connection with parallel skew symmetric torsion, there is some sort of decomposition theorem or classification scheme, like in terms of in terms of the holonomy representation. If it's reducible, then you have an explicit list. If it's reducible, then you get still some sort of submersion where the torsion controls what happens in the submersion. Do you know if it?
Yeah, but the problem here is that you have the complex.
Somehow fit into the scheme, right?
Yeah, but you have to be careful with the compatibility with the complex structure when you construct this kind of decomposition. So.
I see. Thank you.
Okay, thank you.
Okay. Is there any other question? I have one about the standard complex structures.
Yeah.
So you say that on the transversal distribution to the rep vector field, they coincide with the usual complex structure.
Yeah.
But what happens with the reps? Where do they go?
Oh, the reps are here. The reps are here.
Yes.
Sorry, okay, so probably here. You have that so you have that the J essentially preserves the part with the RL, the ribs, and the part in the torus. So they mix all together.
Okay.
So you don't like send, one rib to one rib and so on, but
I see.
they are all mixed.
So they can go to another manifold.
Exactly,
Okay.
yeah. Yes.
But when you have only product of Sasakian manifolds, they must be similar to these Morimoto complex structures.
Oh yes. In the specific case where you have just the three-dimensional Sasaki manifolds, you have that.
Okay.
Yes, exactly. Yes.
Great. Very nice. Okay. Are there any other questions for Nicoletta? No? Well, if this is not the case, let's thank Nicoletta again for a very nice talk.